Hello and welcome to my presentation. My name is Gabriel Guillet. I'm a PhD student at UST, a hybrid entity between Aix-Marseille University and the CNRS, located in France. In this presentation, I'll be talking about my current work, the performance evaluation of a professional cooktop powered by a Scheff reflector. This work is directed by Benjamin Kadosh, Thomas Fasquelle, and Séverine Barbosa. Before to begin, I would like to thank the Région Provençale-Côte d'Azur, the restaurant Le Présage, and the Institute of Mechanics and Engineering of Aix-Marseille University for their funding. The company Le Présage plans to open a restaurant that is innovative in many ways, notably by using solar energy as the main source of power for the kitchen. Their main aim is to serve around 50 customers every lunchtime and some evenings throughout the year. To do this, they built a new solar cooker combining a Scheff reflector with a curved mirror and a cast iron slab. Why use a Scheff reflector? Because it's a flexible dish that allows you to have a fixed focus, so you can cook indoors. The photograph on the right shows their current cooker. The main reflector here focuses the sunlight onto the secondary reflector, which is here, which reflects the sunlight under a simple cast iron plate used by the chefs as a French cooktop. Unlike the plancha, the French cooktop is used with pots and pans, and its surface temperature is not uniform. In restaurants, chefs are used to playing with this. They grill their vegetables and meats in the center, where it's very hot, and simmer their sauces on the sides. To achieve their objective, the restaurant's chefs need a solar cooker in good working order. So before to be able to suggest any improvement, the first step is to measure the cooker's current performance. Before I talk about the overall performance of the system, I'd like to tell you about some earlier work we did in the laboratory on the Scheff reflector. The Scheff reflector was invented in the 1980s, presented to the scientific community in the 1990s, and described in detail in 2010. Since then, many researchers have worked on the Scheff reflector or on a system that includes one, but there is very little experimental work on the heat flux at the focus, and none of it gives detailed data on its intensity and distribution. This is certainly due to the difficulty of making a spatially resolved measurement of a concentrated heat flux. To fill this gap and obtain the experimental performance of our Scheff reflector, we built a test bench. The incoming solar power is estimated using a pyrheliometer, while an infrared camera is used to measure the temperature at the rear face of a receiver. The temperature map obtained is then used to find the concentrated heat flux, which is at its origin. In physics, it is generally easy to determine a consequence when the cause is known, but the reverse is sometimes more complicated. This is the case here. This is why we used special techniques known as inverse techniques, combined with a thermal model of the receiver to obtain the distribution of the concentrated heat flux over the receiver. Here are the results of a measurement carried out on 14 June 2022. By comparing the total intensity of the concentrated heat flux with the solar heat flux collected by the Scheff reflector, we obtain an energy efficiency of 61%. In addition, we have shown that the heat flux distribution can be described to a very good approximation by a two-dimensional Gaussian curve. This allowed us to calculate the size of the heat flux and the surface concentration ratio, which is equal to 40. These results are of interest to the scientific community because the theoretical and numerical work gives very different results depending on the assumption made. This set of data should make it possible to refine the hypothesis and build a powerful model capable of predicting the intensity and distribution of the heat flux as a function of the characteristics of a given reflector under given environmental conditions. These results could also help designers of systems that include a Scheff reflector. The performance of that kind of system are often limited by the thermal losses at the receiver. Optimizing the size of the receiving area as a function of the heat flux distribution would therefore improve the overall system performance. But let's get back to the performance values. The energy efficiency of our reflector is relatively low. The overall reflectivity of the mirrors is estimated at around 80%. We're still looking for an explanation between the 80% and 61%, but we suspect that the mirrors are not perfectly specular and that they scatter some of the sunlight in all directions. Now that we know the performance of our Scheff reflector, what about the overall performance of the cooker? For the purpose of our study, we built an experimental bench similar to the presage cooker. It consists of a Scheff reflector of 8 square meters, which is equipped with an automatic sun tracking system, which is not visible here, a flat secondary reflector, which is here, a cast iron slab, and a big one. They are here. We chose to try the system with a flat secondary mirror instead of a curved one because it is a simple element which is easier to build. I insist on the fact that it is a simplified test bench on which we have already detected defects. Our aim is to obtain an initial estimate of the power supplied by the cooker before making any improvement. So, how did we test it? In order to situate this system in relation to the literature, we chose to follow the test protocol defined by the ASAB standard. The experiment took place in Marseille on 22 July 2022. As the surface of the Scheff reflector was not entirely covered with mirrors, the effective reflected surface was estimated at 7.5 square meters. On the day of the experiment, the aperture surface of the reflector, which corresponds to the blue area in the photograph, was 5.1 square meters. As it would not be interesting or even possible to use a load of 7 kilograms of water per square meter of aperture as specified in the standard, we arbitrarily chose a quantity of 25 kilograms. As required by the standard, water and air temperatures were recorded. They were measured every second using type K thermocouples. As the pot was large, 2 sensors were placed in the water to ensure that the measurements were representative of the whole content. Traditional cookers often have a low thermal inertia, so most of the energy captured is transferred to the water. In our case, the cast iron plate acts as an internal heat accumulator. This is why 7 sensors have been placed on the hot plate to measure its surface temperature. This makes it possible to estimate when the cast iron plate is storing or releasing energy. Ideally, the plate should have a constant temperature through the experiment to eliminate its influence on the measured power. Direct normal irradiance was measured using an Imbrai pyrheliometer, while wind speed was measured using a vertical axis anemometer located close to the test bench. These measurements were recorded every minute and every second respectively. To improve the quality of the measurements, the random measurement noise was reduced using a centered moving average. The moving average window was 10 minutes for water which corresponds to the maximum interval between two measurements stipulated in the standard. For air temperature, direct normal irradiance, and wind speed, we follow the prescription of the World Meteorological Organization. It means 1 minute for the first two and 10 minutes for wind. As the temperatures of the plate are only used as an indication, they are not average. Let's look at the measurement results now. The graph on the right shows the evolution of the temperatures measured by the thermocouples, whose location is recalled on the left. The Scheff reflector was turned towards the sun just before 10. Then the cast iron plate was warmed up and the cooking pot added at 10:42. These events are clearly visible on the temperature curves, here and here. We can also see that the two measurements of the water temperature are superimposed, confirming a fairly even temperature in the water. Moreover, the water temperature rose as expected. Starting from the ambient temperature, it rose rapidly at first and then more slowly. The air temperature, in red, remained stable at around 35 degrees. The remaining curves, representing the plate temperature, all follow more or less the same trend, with the exception of the temperature at point 3 and 7. At point 3, the yellow curve, and the thermocouple was defective. As for the high temperature measured at point 7, here, it could be due to the location of the concentrated heat flux under the cooktop. Indeed, the setup is not perfect, and the sensors seem to show that there is a temperature gradient from 0.7 to 0.9. The hottest point being close to 0.7. As explained previously, in order to reduce the influence of heat storage in the cast iron plate on the results, we have chosen to calculate the standard power only over a selected period when the hot temperature very little. During this period, the average ambient temperature was 34 degrees, the average irradiance was 816 watts per square meter, and the average wind speed was 0.8 meters per second. So now, what is the standard power of the system? The standard power, PS, was calculated in accordance with the standard, then plotted against the temperature difference between water and air, TD. R square is the coefficient of determination obtained using linear regression. This coefficient describes the proportion of the variation in standard power that can be predicted from the temperature difference. The coefficient of determination tends towards 1 if the prediction is perfect, and towards 0 if the prediction is not possible at all. Linear regression gives the red curve and this equation. We can already see that the experimental points clearly show a trend, but also that they are somewhat scattered around the trend line. This is reflected in the value of R square, which is higher than the limit value defined by the standard, but is not excellent either. The standard power found for a temperature difference of 50 degrees is 209 watts. This is relatively slow for a cooker with an aperture of around 5 square meters. The y-intercept of the regression curve corresponds to the power harvested when the water temperature is equal to that of the air. It is when there is no heat loss. It can therefore be used to assess the optical performance of the system. The slope of the curve here indicates the increase in heat loss as the temperature difference increases. By way of example, this coefficient is close to 0 for vacuum tube solar cookers because they are really well insulated thanks to the vacuum and selective paint. Thus, the regression results can be used to analyze the performance of the cooker. By evaluating the performance of the Scheff reflector and the overall performance of the cooker, it's possible to identify the main causes of energy loss and to draw this graph. Sunlight is first collected and concentrated by the Scheff reflector. During this process, part of the heat flux is absorbed by the mirrors. Another part is diffused into the environment, and the last part is reflected in the direction of the secondary mirror. But depending on how well the reflector is made and the location and size of the secondary mirror, some of the heat flux may miss the target. The proportion of the heat flux that reaches the mirror is quantified by the interception factor. The efficiency of this heat transfer was estimated at 61% in the work and mentioned at the beginning. The concentrated heat flux is then reflected by the mirror. Once again, part of the heat flux is absorbed by the mirror. Part is diffused, part misses the target, and the last part actually reaches the target. It is the bottom of the cooking plate. At this point, part of the heat flux is reflected by the plate, and the rest is absorbed. Since we know the efficiency of the Scheff reflector and the standard test gave us the overall optical efficiency, the efficiency of the secondary mirror is estimated at 35%. Finally, the heat flows is transferred by conduction to the cooking pot, but also to its surrounding. With the contents 50 degrees warmer than the ambient temperature, the thermal efficiency is around 28%. The bad news is that this gives a total efficiency of only 6%. The good news, because there's one, is that there is plenty of room for improvement. At this stage of the presentation, and therefore before moving on to the perspectives, I think it's worth taking a step back and trying to draw some lessons about the physics in the system. I would say that radiation is effective at transferring heat from a high temperature body, the sun, over a long distance and until the receiver. It is also practical because it is possible to concentrate the radiative heat flux, and it can be directed as desired by mirrors. But if reflections are necessary, that's the case here, heat transfer is limited by the specular reflectivity of the mirrors and the precision of their orientation. In addition, heat transfer at the receiver is limited by the solar absorption of the surface. Secondly, conduction is interesting if we want to transfer heat across an interface, which is also the case here with the hot plate and the pot. But conduction is limited by the conductivity and diffusion of the materials and by the thickness of the interface. Finally, convection with the air is a phenomenon that needs to be reduced in this case, as it contributes to heat loss from the system. This can be limited mostly by insulating hot surfaces. So, what are the perspectives? First of all, I would like to mention that this work is in progress and that the experimental results need to be consolidated. In particular, we would like to carry out more measurements to assess the variability of the results. In addition, we are wondering how the volume of water and the number of pots should be chosen to give a representative value of the system performance. There are also questions about how the thermal inertia of the plate should be taken into account. Secondly, several options have been identified for reducing optical losses. The specular reflectivity of the reflective material should be as high as possible, and the mirrors should be oriented with particular care. In a new design, non-imaging optics could help to improve the interception factor, but the number of reflections should be kept to a minimum. Finally, as far as the thermal aspect is concerned, the two sides of the hot plate must be studied separately. The bottom should be insulated everywhere except in the reception area. Greater concentration would enable an even larger surface area to be insulated. Next, the use of selective paint and window would reduce losses. At the top of the plate, a usage approach should be carried out with the chiefs to see how technical solution and changes in usage could be combined effectively. Lots of things to do. That's the end of my presentation. I hope you enjoyed it, and I thank you for listening. I will be happy to answer any questions you may have during the next discussion or later by email. Gracias.